Okay, in this mini lecture, we are going to look at molecules in terms of their motion. So matter in terms of its motion, not macroscopically like we did in first semester physics when we look at kinematics and forces and momentum, but microscopically. We know that atoms within matter are moving, right? Solids, kind of go back to that atomic theory of matter in previous lectures. Solids are kind of wiggling around a fixed position, liquids are moving a little bit more, and gases are moving all over the place. And that random motion of matter, Brownian motion of matter, is how we're going to look at matter in this mini lecture. So the motion itself. And the great thing is that that motion follows classical mechanics. Now, there's a lot of particles there and a lot of motion, and the randomness of the motion itself would make analysis of any one particle incredibly difficult. But if we look at statistics, averages, and distributions, we can actually get a really good approximation of how matter is moving and how we can use its motion to describe its behaviors. So we're going to do that in this mini lecture. We're going to explore the ideal gas law again in this mini lecture using this idea of the kinetic theory of gases. So how can we take that ideal gas law and look at it in terms of the object's motion? Because the ideal gas law, as we learned in that mini lecture, kind of governs the situation for gases. So we're gonna take gases, ideal gases, and then we're gonna look at how that's related to the motion. All right. Well, in order for us to do that, we need a few assumptions. Okay. One, we know that gases are free to move, and that motion is going to be described with classical mechanics. Okay, and in this statistical way. But there's some assumptions that deal with that. In order for us to really be able to use statistics to describe this motion, we have to have a lot of numbers, large numbers of molecules. So our first assumption, we're going to put our assumptions up here. Okay, our first assumption is that we have large numbers of molecules. Okay, that's assumption number one. So we can actually do decent statistics, and these statistics describe the behavior so we know we have those large numbers. The second assumption is that the molecules are really, really far apart from each other relative to their size. Now we know if I have a container that they're not that far apart from us in the macroscopic world, but the distance between molecules is huge relative to the very, very tininess of a molecule. And so that's the second assumption we're making, that the distance between molecules is much, much larger than their size. Okay, so much, much larger than their size. We are going to focus entirely on the classical mechanics and that behavior. We know as molecules get close to each other, they do interact with each other, have forces with each other. Those forces, of course, have energy, but the energy of those attractive forces is much, much smaller compared to the kinetic energy of the motion itself. So the kinetic energy of the motion is much, much greater than the intermolecular forces. Okay? And that's important, that those forces don't do a whole lot in our gas description that we're going to look at in these ideal gases. And then the fourth thing that's also going to be very important for us is that we are dealing with perfectly elastic collisions. So these molecules are certainly going to interact with one another. They're going to collide with one another. They're going to collide with the edge of the container. But they do so in a way that's perfectly elastic. No energy is lost. No kinetic energy specifically is lost in a perfectly elastic collision. So again, if that's not familiar, that terminology is not familiar to you, go back and check out our momentum videos and collisions, and that will remind you about that perfectly elastic idea. So these are the assumptions that we're going to be making as we explore this idea of kinetic theory for our molecules. All right, so we're going to start, and this is going to be a pretty big derivation, kind of following through we're going to pull from a lot of different areas. We're going to talk about a single molecule, okay, and then we'll expand that to multiple molecules, and we're going to talk about that molecule moving in a single direction. You can also think about it as its component we're going to look at one of the components of its direction. So the molecule could be moving in 3 dimensions, have an x, a y, and a z component to its motion. We're only going to focus on one of those dimensions right now, and we know that's appropriate because whenever we analyze motion, we separate the directions. So that's all we're doing with this analysis. So let's imagine that we have a molecule, and it is going to hit the side of a container that it's in. Let's make both sides of the container. This is a really small container, a really big molecule relative to it, but I think you'll get the idea. So it's going to, let's say it's moving, and we're going to use the x direction, so the horizontal direction is our dimension. It hits that container end, and it of course bounces back. Now with a perfectly elastic collision, the velocity change of that molecule is only in direction. So our change in momentum is going to be 2 times the initial momentum. And this is only in that x direction. And again, go back to those videos if you're not sure why that works out that way. So this is, momentum, remember, is our mass times our velocity. And again, this is in that x direction. So I'm going to keep that subscript x. And I'm going to use this curly QV because we're going to deal with volume in a little bit. And I want to make sure we're separating our variables. So then that's 2 times m times that velocity of that particle. Okay, so that's the first thing that we want to pay attention to. Now this particle is moving. It's moving very fast, right? It's going to be hitting that wall a lot of times, forces over a lot of times. The change in momentum is force over a lot of times that it's going to be hitting that wall. And the change in time, the time it takes, is going to be related to how far it has to go all the way back to hit the other side and come back. So the change in time is equal to 2 times the length of our container, right? Divided by how fast it's going in that direction. So that's how long it's going to take between each one of its forces, okay? So 2 times the length divided by how fast it's going. Velocity is just distance over time, so time is distance over velocity. Okay, so we know that our change in momentum is equal to the force times this change in time. That's our impulse relationship. So the force is equal to our change in momentum divided by our change in time. So now let's use the relationships that we have here to get that. We have our change in momentum of 2 times the mass times the speed in the x direction, divided by our change in time, which is 2 times the length over the speed in the x direction. So if I simplify that, I end up with the mass over the length times the speed in the x direction squared. So this is the force that is due to a single molecule. So this is the force of one molecule. Okay. Now, what if I have lots of molecules, which of course we do? Well, the force of any one, if I want to look at the overall force, I'm just going to keep adding those up, right? Force 1 plus force 2 plus force 3. So if I were to write what that looks like, and I think I can fit one more down here. So the force of all of them together is going to be the mass times the length of one molecule plus another molecule, all the way to the number of molecules I have. Okay, so that's the force of all of the molecules. Just all of them, all the way to n. Okay, well, let's talk a little bit about averages, all right? We know that the average of anything is adding everything up, dividing by the total number that we have. So the average velocity of all of these molecules, the average velocity, the average squared velocity of all these molecules is equal to the sum of them all the way to n, oops, divided by the number of molecules I have. So when I do a little rearranging, I have n times the average velocity squared is equal to the sum of all of the molecules. Okay, so that's a little math reminder of averages. But now I can use this down here. So I can substitute, put my force up here. My force is equal to m over L times the sum of the squares, which is also n times the average in that direction. Okay? All right, so this is in one direction. And we know that we would do the same thing in the y direction and the same thing in the z direction, right? We also know that for random motion, the speed in any one direction is the same as any other direction. It's random. So on average, the speed in one direction is going to be, on average, the speed in the rest of the directions. Which means the average speed in the x direction is going to equal the average speed in the y direction, which is going to equal the average speed in the z direction. Which means that the average speed squared in the x direction equals the average speed squared in the y direction equals the average speed squared in the z direction. That's not a stretch. And so the average speed, okay, we know that. We also know that if I were to define the average speed in general of a particle with a speed whose component is x, y, and z, I'd use Pythagorean's theorem. The average speed squared is equal to the average speed in the x direction squared plus the average speed in the y direction squared plus the average speed in the z direction squared. And if all three of these are the same, then the average speed is equal to 3 times the average speed in the x direction. Aha! Here I have my average speed in the x direction. I can substitute in. This tells me that the average speed divided by 3 is equal to the average in the x direction. So I can rewrite my force equation in terms of just the average speed, okay? The magnitude of the velocity vectors in any one direction. So times n times 1/3 the average speed squared. Okay? One more thing. We talked about sneaking in the ideal gas law, right? That involves pressure. I'm going to pull the title off so I have a little bit more headroom here. Remember, our ideal gas law says PV equals nRT. So pressure is important. Pressure, remember, is also equal to a force divided by the area. So the pressure times the area is equal to the force. Pressure is force times area. So I could write my pressure, my force, equal to the pressure times the area. Now we also know that the volume of a container is equal to the area times the length. Length times width times height. Let's use a square. Length times width times height, and the length times the width gives me the area times the height would give me the volume, or whatever variation you want, but the area, two sides, multiplied together, times the third side. So I can rewrite this equation, divide both sides by the area. Now area and length are in the denominator, and I have the pressure is equal to M times N times the average velocity speed squared, over 3 times the volume. This is the pressure in a container based on the volume. Okay? All right, we're gonna keep going. I just want to make sure my nomenclature is right. I'm gonna rearrange this to make it look a little different. We're gonna bring V out because we want to go back to that ideal gas law. And we end up with PV equals 1/3. I want to put it in the right order. Times N times M average velocity speed squared. That doesn't look like PV equals nRT yet. But we have this PV here. But if this is pressure times volume and this is pressure times volume, that means that this equals lowercase n, capital R, T. PV equals nRT, PV equals this. Okay, I need to do some erasing because I'm running out of room. I'll let you kind of absorb some of that. Over here, we need to do some more derivations and remind ourselves of some few other things that maybe you're recognizing. I hinted this idea of energy, and maybe something looks similar to energy for you. All right. I think if I were in a classroom with whiteboards across the front, we would be using the whole board for this particular introduction and derivation. All right, I'm going to rewrite this up top here. We have PV equals nRT. I'm going to write them all. We have PV equals 1/3 capital N M average speed squared. Okay, we have those two right now. All right, a couple of things that we know. We know about kinetic energy. We know that kinetic energy is equal to 1/2 mv squared, right? Okay, 1/2 mv squared is our kinetic energy. That's going to come into important because I see this mv squared. That makes me go, oh, wait a minute. Kinetic energy is related to mv squared. So, and I'm all interested in how this all relates to motion. So let's remind ourselves that that n, little n, remember is number of moles in our ideal gas law. And we know that the number of molecules, capital N, is equal to the number of moles times Avogadro's number, N sub A. So Na is equal to Avogadro's number. Go back and look at those lectures to remind yourself of that. That tells us that N is equal to the number of molecules over Na. So I'm going to go back here. And we have, which one do we want to look at? We have PV equals nRT. I'm going to substitute in for that. I have PV equals the number of molecules over Avogadro's number times R times T. Now, R is a constant. Avogadro's number is a constant. And it turns out the ratio R to Avogadro's number is also a constant because it's two constants, so it has to be. We call that Boltzmann's constant. Okay. R divided by Avogadro's number. Which means that PV equals NK times T. All right? So let's use that information. Let's use that information. I'm going to go and erase these. I'm going to keep my kinetic energy up there, though. That's going to be important in a minute. All right. So if PV equals NKT and PV equals 1/3 NMV squared, we've got something here. So let's go PV, I'll just rewrite them, equals NKT, which equals 1/3 N M average speed squared. So I've just taken this relationship for PV and this relationship for PV and set them equal to each other right here. That tells us that K times T, I divide both sides by N, KT equals 1/3 MV average squared. Now we're going to pull this in. 1/3 MV squared is equal to 2/3 times 1/2 M speed average squared. So I just used a ratio here. This is equivalent. 2/3 times 1/2 MV squared is 1/3 MV squared. Okay? This is my kinetic energy. So that tells us that KT, Boltzmann's constant, times the temperature is equal to 2/3 times the kinetic energy. This is awesome. Because what this tells us is that the motion of particles are based on the temperature. And all that you've learned, that conceptual idea of as we heat things up, the particles start to move faster is right here. That the temperature dictates the amount of kinetic energy an object has, molecules have. And that's really cool. Kind of comes full circle in this idea of the ideal gas law. And it goes back to when I first introduced the idea of temperature. Now, this T is important. We want to keep in mind, and you know this from our discussion of the ideal gas law, that this is absolute temperature, right? In Kelvin. And when I first introduced that idea, go back to that temperature video, and we talked about the Kelvin scale. I said at 0 Kelvin, all motion ceases. Absolute zero. And I just threw it out there. Well, here it is. When the temperature is 0, there's no kinetic energy. All motion stops. Okay? Now this is all cool because it's the energy of a gas. The energy of gas is related to the temperature in this way, and we're going to use that relationship. It also leads us to think about, well, how fast, this is the energy, but how fast are particles actually moving? And so we're going to look at the distribution of motion of those particles, molecules, atoms in a gas in the next lecture. And we look at the distribution of speed in this kinetic theory of gases. All right, lots of derivation. I don't typically do derivations. This one's kind of fun. That's that we explore this idea of describing matter in terms of its energy and its motion. All right, good job.